The electrolysis of molten aluminum chloride for 2.5 hours with an electrical current of 12 amps produces how many grams of metal? Good question. What do you think we need to solve this problem? Delta G thing, well, something that's in that equation you definitely need. Moles, yeah, that's going to be good. We're going to need a molar mass of aluminum. Let's see here. What does the periodic table say? It's almost 27, right? All right, close enough. What else do you think we might need? Chlorine's not important. It's going to be a spectator ion. What we need is a chemical equation. We need a half reaction. So what's the charge on aluminum here? Yeah, 3 plus, and you can see 3 chlorines. So we're going to have something that looks like this. Aluminum, 3 plus some electrons, goes to aluminum metal. To charge balance this up, how many electrons do I need? 2 or 3? How about just 3? Now there's one other thing we need, and Caden was getting close to it. This number here called the Faraday, and 1 Faraday is equal to, what is it, 96,485, and we're going to use coulombs per mole of electron. Now, why do we call this a Faraday? Very good, and as promised, my Wikipedia bio, here is Michael Faraday. He lived from 1979 to 1867, and physicist and chemist, and he contributed to the study of electromagnetism and electrochemistry. That's what we're really excited about today, is electrochemistry. His main discoveries include the principles underlying electromagnetic induction, diamagnetism, and electrolysis. So what? A square cigar? He's holding a special glass rod that I could have used another photo, but this photo had the most detail. I'm always disappointed I can't dress like this today. But interesting things, he discovered benzene for the organic chemist, kind of invented a Bunsen burner, and came up with terminology such as anode, cathode, electrode, ion, and I deleted where he was not real formally educated. He was kind of self-taught. And then here's something new that I found out in my study. Albert Einstein kept a portrait of Faraday on his study wall along the sides of Isaac Newton. You all know who he is. What about James Maxwell? Maxwell took a lot of the things Faraday came up with and came up with Maxwell's equation, which described electromagnetic radiation and magnetism in concise mathematical terms. And they said Faraday only had like trigonometry and basic algebra. And Ernest Rutherford, do you know who he is? Please. Yeah, the gold foil experiment. Well, in my office over here, I only have a little photograph of me and a physics teacher who quit probably 18 years ago when we went water skiing at Alcova someday in November, and I'm holding up a newspaper to say it's November, and we went water skiing, and a picture of Groucho Marx. So I need to do some work on. All right. Well, we need a few more. One more thing before we go there, though. We have some options. This was a multiple choice question. These might be our options. What we need is a definition of an amp. And 1 amp is equal to a coulomb per second. So what is a coulomb? It's a measure of electrical charge, and there's some definition about 2 plates so far apart and a certain amount of force due to the charge. And I always tell students, ask Jared or Dr. Drew what a coulomb is, but it's related to electrical current. So now we have everything we need to solve this problem. So looking through here, there's a couple numbers I could start with. Here's something I tell students they don't like to do. I just say choose a number and start and see if it works. And if it doesn't work, start over. And how will you know if it doesn't work at the end? Your units. Yeah, your units will be incorrect or... All right, so hours. 1 hour, 60 minutes, 1 minute, 60 seconds. Could have just gone 3,600 seconds per hour. All right, now I see the unit of a second. I think I want to go, should have worked this before I walked in here. What I like to do over here is tell students a second times an amp equals a coulomb. So we got seconds. So if I put amp here, and then I find coulombs, now I have to look at my balanced chemical equation, and I see 3 moles of electrons for every 1 aluminum. So the only thing I'm not real satisfied with is this funky thing here. I'm gonna get rid of it. I like to just go up here and say 1 amp is a coulomb per second, and put 12 coulombs per second. It just seems more logical to me to do it that way. All right, then we can look and see if our units do what they're supposed to. Hours goes away, minutes goes away, seconds, coulombs, moles of electrons, moles of aluminum, and into grams of aluminum. Here we go, 2.5 times 60 times 60 times 12 divided by 96,485, divide 3, multiply 26.98. My calculator spits out 10.1 grams of aluminum. Any questions? So I wanted you to see this because in lab we calculate the Faraday, and we're going to have 2 half reactions. One you've seen before with the first lab. 2 protons and 2 electrons make 1 mole of hydrogen gas. How many minutes will it take to plate out 2.19 grams of chromium metal from a solution of chromium-3 using a current of 19.5 amps in electrolysis cell? So you got your custom Harley and you want to chrome plate your kickstand. You take it to a electroplater, and there's a electroplater in town. Any town this size has a place where you can have various electroplating done. And so they take your kickstand and make it the cathode, and they probably buy bags of, I don't know, chromium, some soluble chromium salt, hook it up, run a current, and you get a nice chrome-plated kickstand. So which number should I start with, do you think, in this problem? Yeah, we can set up an equation. Chromium-3 plus some electrons goes to chromium metal. How do I balance charge? 3 electrons. I'm going to just start with this mass. To me, that seems the most logical. Everything in chemistry proceeds through the what? Mole. Look up at your periodic table. 51.9199. So here's our balanced chemical equation. We've converted mass to moles. If you have a mole map, which I sometimes give students, we have this thing called the mole ratio. And what do we want to put in here? Absolutely. And at this point, it doesn't matter. We could put our +3 there. We could leave it as a metal. So just our standard stoichiometry at this point. And then I know that for 1 mole of electrons, that's this 96,485 coulomb. And maybe off to the side here, I said I like to take the word amp and just replace it with a coulomb per second. And like a good student, I go back and I read the whole question, and it says we need minutes. So this should get the job done. 10.4 minutes. Any questions? So we're going to leave free energy. Not really. So what is Q? Yeah, the reaction quotient. It looks just like K, the equilibrium constant. Q is just when we're not at equilibrium. And I said you don't want your battery to be at equilibrium because you want it to spontaneously generate power, and it does so with a spontaneous chemical reaction. And the battery is set up with 2 compartments, cathode and anode compartment, and the only way the reaction can occur is if you connect a battery to the 2 sides, and then that's where you get this free energy that can do some work. So this is a standard free energy change for some reaction plus RT times the log of Q. So Q is the reaction quotient. It's that equation we looked at the other day that said delta G was equal to minus NF times E. We can come up with something like this. If we know the standard cell potential and the temperature, and R is the constant, and we know something about the concentration of our reactant, we can get something like a voltage. So that previous equation, we divide both sides by moles, electrons, and Faraday's constant. Whoops. And then for some reason we say let's not work in natural log, and we get down to a base 10 logarithm. We get something that looks like this. The voltage we read is equal to the standard voltage minus 2.3 RT divided by NF. Well, if we plug in standard temperature at room temperature, we can simplify this a little more. Or if you take this thing here, that becomes 0.0592 volt, and so we can kind of get rid of the Faraday constant by dividing Faraday's constant in there. The one that had the other units, not coulombs per mole of electron, but the coulomb, joule, and we get this equation here, which is a real powerful thing. It says if we read a voltage and we know the standard voltage, we can know something about Q. So it might be interesting to build one of these things, but it shows this concept. So here's a nickel electrode, here's a nickel electrode, and we have 0.5 molar, maybe nickel nitrate in each one of these. And it reads 0 voltage. Makes sense? Over here, we have 1 molar nickel nitrate, and over here we have 0.001 molar nickel nitrate. So there's this difference in concentration. So Q causes this thing to develop a voltage. So you're not fascinated yet. So here is the fascinating thing right here. This thing is called a Clark's oxygen electrode. Who was Clark? He was a cardiac doc. So when you get surgery, what do they monitor? All these blood gases. They monitor your oxygen level. The anesthesiologist, if he gives you too much, you don't breathe enough, your oxygen goes. They got to keep tabs on that real time, and they don't have time to go do a titration. So what do? They use electrochemistry. And so this thing can be manufactured real small, and they can shove it up your vein. And there's an electrochemical cell that has a silver wire and some silver solution. And then this other electrode is based on oxygen concentration. And here's a semi-permeable membrane. The oxygen gas in your blood can diffuse through there. Here's this platinum cathode. This reaction happens, develops an electrical potential. So my wife's a med tech, and she works at a clinical lab in town, and they have machines, and she'll typically have to replace electrodes and run standards. And when you get your blood serum drawn, a lot of things in your blood, they measure electrochemically. A lot of like calcium, potassium, a whole bunch of stuff. So this is all based on the Nernst equation. Well, now you're all ready for lab, knowing about the coulomb, Faraday's constant, and what an amp is.